Chinnasamy sir started.
Started, but it's saying waiting for Kumaraguru College of Technology like that. Yes, it started, ma'am. Now.
We can start, Sasikila ma'am. We can start.
Okay, good morning. Good morning to one and all present here. We extend our warm welcome for your participation in the 1 week short-term training program. It's jointly organized by Institution of Engineers.
Aline?
Yes, ma'am.
Aline, one second. Nadarajan sir has to join. Kindly wait for 2 minutes.
Okay.
Hello. சொல்லுங்க நான் ராமோகன் சார் ஜாயின் பண்ணிட்டாரு நீங்க
சொல்லுங்க. சொல். Alan, you can start. Everybody joined, I think so. Dr. Natarajan sir also joined.
A very good morning to one and all present here. Institution of Engineers India, Coimbatore Local Center, in association with KCT ECE IEI Students Chapter, organizes a 1-week STTP on Artificial Intelligence in Healthcare. We welcome you all for this 1-week STTP. Now, I invite Dr. P.R. Nadarajan, Chairman, IEI Coimbatore Local Center, to deliver the welcome address. Over to you, sir.
Can you hear me? Hello?
Yes, sir, it's perfect.
Respected friends, I welcome you all for this program. On behalf of the Institution of Engineers India, Coimbatore Local Center, and on behalf of Kumaraguru College of Technology, I extend a wholehearted welcome to I extend a special welcome to Dr. Sajith, Kecheril, Sadanandan, who has been kind enough to be the chief guest on this day and deliver his address. And I also welcome all the professors, students, and participants of this program. It's very interesting on this occasion to note that this year of 2020 is going to be very interesting for our youth of India, especially as to how they are going to take up their responsibility of managing the whole of the world. It's very interesting to be young in India at this extraordinary time. Today's program will present ideas to all the researchers and expose on the current scenario of artificial intelligence in healthcare. I do hope this training program could also be utilized as a platform to exchange ideas on artificial intelligence in healthcare management. Once again, I extend a warm welcome to everyone. Thank you.
Thank you, sir. Thank you for welcoming the gathering available in Zoom platform as well as the YouTube live streaming. Thank you, sir. Now I invite Dr. Sasidh, Associate Professor, Department of ECE, Kumaraguru College of Technology, to introduce our chief guest. Over to you, ma'am.
Thank you, Alin. Yeah, very good morning to one and all present here. Artificial intelligence and computer vision technologies are rapidly revolutionizing the medical industry around the world. Applications of artificial intelligence in healthcare are endless. It offers a number of advantages over traditional analytics and clinical decision-making techniques. Deep insight about artificial intelligence and computer vision is an important requirement for developing computer-aided diagnosis systems. Today, we have Dr. Sajith Kecheril Sadanandan, an algorithmic development engineer in Q-linea, Uppsala, Sweden, to provide a better understanding on image. Pleasure to introduce him to this gathering. Dr. Sajith has completed his BTech degree in Electronics and Communication Engineering in College of Engineering, Karunagapalli, Kollam in Kerala State during 2001. Then he completed his MTech degree in Computer Vision and Image Processing in Amrita Vishwavidyabhidam, Kollam in Kerala. After that, he has received his doctoral degree in Computerized Image Analysis in Uppsala University, Sweden in the year 2017. He is a well-experienced person in the field of medical image processing, algorithm development as project engineer and also a senior project engineer in CDAT. Presently, he is working as an algorithmic development engineer in Q-linea, a biotech company innovated solutions for healthcare providers, enabling them to accurately diagnose sepsis in the shortest possible time. I believe he is an appropriate person for handling this session. I hope the participants will gain good knowledge in the area of image analysis using deep neural networks, which will be much helpful in understanding and comprehending the advanced problems in healthcare. I thank our KCT management and Institution of Engineers India, Coimbatore Local Center for giving me this opportunity.
Thank you, ma'am. Now I invite Mr. Sajith Sadanandan, Algorithm Development Engineer, Q-linea, Uppsala, country, Sweden, to deliver his chief guest address. Over to you, sir.
Thank you so much for those kind words. I think there was some problem with the audio, so it was a little bit mix of several people talking. I hope now it's clear to everybody. So it's quite So when it comes to AI, it's with the current standard, it's not very clear what actually AI is. But with the current limitation of, even though we don't attain the real AI, we can use the tools that are available to solve many problems that we have today in the medical field also. So AI is quite popular in the media, and we all hear about self-driving cars and disease diagnosis and many other fields like MRI, CT, or in the microscopy, or even in thermal screening, which is quite widely used nowadays for human body temperature, which is a very good tool as well. Another area of where the artificial intelligence or the tools of such tools are applied is for personalized cancer treatment, where you have like a specific treatment for a particular person. It's not like a common treatment for everybody. It's like it's quite targeted to each and every person. And these are like new fields which are coming up just because we have very good tools available, especially this AI tools or deep learning tools available. And these are like areas where we couldn't think of some years ago, maybe. But with these tools, we are able to come up with or approach problems in a new way and come up with the new solutions. And I think it's a good time to have these kind of tools and explore more in this field. I think it's quite an interesting time to live.
Dear
actually.
sir, sorry, dear sir, sorry for the interruption. The video is not. We were not able to view the video.
Hello, sir. No video is presented. No.
All the participants are asking for the PPT.
Okay.
So that.
Yes, sir.
Okay. Now you are okay, sir. We were able to see you, sir. Very good morning, sir. You can continue, please.
Okay.
Well, sir, you can proceed.
One of the important reasons that we can use these tools is because we have a very good computation resources available today, which was not quite possible some years ago. So in a sense, it's quite a nice time to have these tools. Also, the medical community has evolved quite a lot, and they kind of accept the new technologies and it's actually a little bit annoying to hear myself quite often. Sorry for that trouble. I don't know how to solve that anyway. So I think that's all I have to say. Probably the next person can speak now.
Thank you, sir. Thank you for the mind-provoking address. Now I invite Dr. H. Ram Mohan, Honorary Secretary, IAI Coimbatore local center to deliver the vote of thanks. Please, sir.
Yes. Thank you. Good morning to all. It's my great pleasure to deliver the vote of thanks. We thank our IEI Coimbatore Local Center Chairman, Dr. P.R. Nadarajan, for his welcome address. Thank you, sir. We thank Dr. S. Sasikala, Associate Professor, Department of Electronics and Communication Engineering, Kumaraguru College of Technology, Coimbatore, for her introduction to the program. Thank you, ma'am. We thank today's chief guest, Mr. Sajith, Kecheril, Sadanandan, Algorithm Development Engineer, Q-linea, Uppsala County, Sweden. Thank you so much, sir. We thank the principal and the management of Kumaraguru College of Technology, Coimbatore, for this wonderful arrangement of this STTP program. We thank the whole team of faculty members for their great effort in making this event as a successful one. We thank all the participants of this program. Let this be a successful program for all the participants. Thank you, one and all.
Thank you, sir. Now I invite Dr. Sajith to take over the session. Over to you, sir.
Thank you so much, Aline, and others for those kind words. We'll just start the screen now. I hope you can hear me. So it's not exactly what it's not specifically AI that is what I'm going to talk today. It's more like the image analysis.
Hello, sorry for the interruption, sir. Sir, little bit audible, sir, little bit louder, sir.
Industry, quite a lot of
Your
image analysis
voice
happening,
is not
and,
much audible.
The core behind modern AI is something called deep neural networks. So,
hello, sir.
We will discuss a little bit more about deep neural networks and
excuse me, sir.
mainly how they work and what we can do with them and things like that. And this will be more like a introduction section, so you can get a hint of how things are done, and then you can build on that, improve on, and I will give some further reads and links to the end of this slide so that you can go through them later if you're interested. So I'll have this presentation divided into introduction, building blocks of AI networks and its components, how we can train them, and a little bit about the implementation. I think there is no need for this slide because it was already done by the other person. Yeah. So I have a little bit of a disclaimer. Everything is that I present in here is my own personal view, and it's not the view of Q-linea, the company that I work with. And I'm not sponsored by any of the companies or technologies that I will be mentioning here. And all copyrights and ownership belong to those companies, to the respective ones. So we will start with some applications. So what we can do with the deep neural networks or the AI components. So we can, in the medical field, we can do something like a cell classification. If it's a benign means it's non-cancerous, or malignant means it's cancerous, so we can differentiate between cancerous and non-cancerous cells, and or if it's like a high throughput cases, like this is called a zebrafish, and it's one of those model organisms that is used for drug screening and high throughput screening systems, because they grow very quickly, and they are like quite transparent, so we can see exactly what is going on inside those organisms. So sometimes the idea is to see if due to some treatment with a drug, the organism is affected or not. In this case, this is like a little bit of bent to one side, and if it's untreated, it's like a straight. So this is one example of a classification problem that we can address with the neural network. Or we can go for some segmentation, like we have a bunch of cells and we want to identify each and every cell in them to see how they grow over time, and how by giving some antibiotic, if these cells are dead or are they still growing, and do more experiments on them. So this is another example of this. Or it could be more like a common like a computer vision application where we go for object detection. So we give an image, like an example image like here. So in this image, you can see there's a dog, there's a bicycle, there's a truck or a car in here. So the idea is to identify every object present in the image. And that's basically object detection. So this is quite popularly used in self-driving cars to identify different objects, pedestrian, or it's a car in the front, or it's coming towards you or moving away from you, things like that. So this is another popular application. Even though this is more like a computer vision application, we tune a little bit of the data, and we can apply them in the healthcare domain, also in the medical field. Also, another application is like super resolution reconstruction. So here we have a very low resolution image, and we use some neural network to recreate the original image. The ground truth here is the actual image, and this is the one we created. So it's a very, very close to the real image. So these are like interesting applications that we can apply neural networks. Or we can generate more images, new images. Like these people does not exist. They are actually generated by a neural network. They are like a photorealistic images of people. So these have like quite a lot of potential to generate new images. So if we come to the medical field, it will become like a more data, generating more realistic data for probably can be for training of network or other aspects, or more or other like a simulating of some problem, something like that. Or another application is like a popular one is like face transformation. So you can see how a person looks like after like 10 years, 20 years, 30 years. So give a source image and you can get different images. These are like a popular apps available. You can these are so much. So other one is like a style transfer. So you have this source image in the first row, and another set of image in the first column. And you take features from one image and combine it with another image and create a new image here. So this matrix is a combination of features from these two, this column and this row. So we can mix and match and find different new set of data actually. So these are all based on a type of neural network called generative adversarial network, which is a little bit popular nowadays. So when all this neural network and its hype started, so there's a competition called the ImageNet Large Scale Visual Recognition Challenge, or ILSVRC, which is like it contains 1,000 classes of images, and there are like 1.2 million images for training. And you give when after training your system, you give one image and classify it into one of these 1,000 classes. And you can see that between 2011 and 2012, there is like a huge jump here. So in 2011, it was done by traditional image analysis tool. And what actually happened in 2012 is like a group applied something called convolutional neural networks or deep neural network in this problem, and they got like a more than 10% improvement in this particular task. So people realize that this is having a huge potential, like more than 10% jump is like is very good, very like huge in this field especially. And so afterwards, all of this competition is done every year, and then all these competitions are won by some sort of a neural network afterwards from 2012 onwards. So that's the time when this deep neural network or AI hype again started. So it has reached a point where it's like the error is 3% or less. So 3% is some sort of a threshold. So it's like the human, the best performing human can make like 3% error. So it has reached a human like capability, and now it's like a little bit below that. So it's getting to the region of superhuman capability. It's a little bit debatable what is superhuman. So, but it's still like a better than an average human. So that we can definitely say. So on this particular task, not in all tasks, but for this one. So we will go to the building blocks now. So it all come from something called a neuron that is in the human body and in other animals. So we know that a neuron has dendrites, mini dendrites, small, like hand-like structures like this, and then there's like an axon. What the neuron do is like it will receive some signal and do some operation in this nucleus, and then after processing it, it will send a resulting signal to the axon, to the other neuron, and the next neuron repeat the same process. So that's how roughly a actual neuron works. And we have some sort of simulated this neuron into something called artificial neuron. In the artificial neuron, we have some inputs like x1, x2, and we have some weights or parameters, okay, this w1, w2. And what we do is we get one input, multiply it with a weight, and then, similarly we multiply each and every input with some sort of weight and add those values, like the summation here. And after summing up, we have a single value. And this is passed to a function called, to another function called activation function. I've represented as f here, and it will give an output. So again, this output go to another neuron and goes on like that. These activation functions are usually some sort of non-linear function. So some of the examples are like a tanh function, which goes from -1 to +1, or it could be a sigmoid function, which is going from 0 to 1, or it could be a rectified linear unit, which is like we cut all the values less than 0 and pass only those values, 0 or above, or positive values, 0 and positive values. That's how a rectified linear unit works. This is one of the most popular activation functions used nowadays. So what is a deep neural network? It's not well defined what is actually a deep neural network and how deep it should be. So roughly we can say that for a deep neural network, there are several layers. What is called the input layer, an output layer. So input layer is the input layer where we give the input to the network. And output layer is the one where we get the output from the network. And in between the input layer and output layer, there are several layers. They are like hidden from outside. So we cannot see them directly from outside. So they are called hidden layers. And a deep neural network, there are more hidden layers. So if there are like say 5, 10, maybe 100 or 1,000 layers, then it's a deep neural network. So if it's not having that many layers, like maybe 1 or 2, then it's a shallow network. That's what we have used for several years. Now we use neural network with many layers. So whenever you hear the term deep neural network, you mean that you understand that it's having more hidden layers, several hidden layers in the network. So coming to the types of deep neural network, there are different types of deep neural network. This is like just a rough classification of types of neural network. One is called a convolution neural network, and the one is called a recurrent neural network, and then something called autoencoders. Even though we can classify them, there is no like a strict rule of creating any deep neural network with only one type. We can mix and match any of these and create a new type according to our problem. So we will focus more on convolution neural network because it's most widely used in the image analysis task. So they contain convolution layers. So we know the convolution operation, like just like we multiply some weights with some input and then add them, and that's convolution. So and they have only local connections. So then they only connect. So when we move this green, assume these green are like the weights, and there is only connection in the local neighborhood here. So this red neuron, this red node is connected only to these three, and not to these ones. So when we move this downwards, this one get connected here and not here. So only local connections are there. So it's not fully connected like we have seen here. Like here, everything is connected to everything else before it. So here we have a lot of connections. So this is connected to this one. So that's not the case with the convolutional network. Only local connections we have, and the spatial relationship is preserved. That means if there's a change in the top part of this input, it will be reflected only in the top part of this layer, not here. So anything happening here will be available here. Anything happening here will be available here. Something like that. So the spatial relationship is preserved. So it's a very important feature in our image analysis. And another thing to note is the same weights are shared among all these different parts. So the same three values are here. The same weights are applied on this part. So the parameters are shared, and it's widely used in analysis. And when we say images, it's not 1D, it's like a 2D or more. And in the same applies here also. So we have like this 3x3 filter that's moving over the image, and you get the output here in the next layer. It goes on like this. So here also the spatial relationship is preserved. So anything happening here is available here, and anything happening here is available here. So in the convolutional neural network, everything is applied in like a 3D convolution. So each layer has several like a depth also, like in this direction. So in this neural network, every like after so we can see this green filter that is moving in this three dimensions, like in the row, column, and the depth dimension. You get a single value at this next layer. So it's only in one of this image. So these images are called the feature maps in neural network terms. And all these features, these weights, these green weights are learned from the data. So when we train, it is learned. These filters are learned. We don't have to manually give these values. And when we have this matrix or this filtering operation, it can be applied as like a fast matrix multiplication in GPU even, like that makes everything faster. And we know that when these are implemented as like tensor multiplications or addition, tensors are matrices of more than 3 dimensions. So we can have many filters like this and apply them in a faster way. And we can go for hierarchical feature extraction. That means, so you have this, you apply one filter, you get a value in this layer, this output feature map, and the next, the yellow filter, you get the output in the blue, like in the feature map below this one. So we can apply the same operation on the next layer. So then we have we extract more features on top of new layer. So that's how this hierarchical feature extraction happens. Probably we think that convolutional networks are quite new, but we can see from even the convolutional networks are applied even at as early as 1989. So it's not very popular. It's not like a new thing, but only the way they are implemented is different than those old days. And another like a recent one is something called AlexNet. This is the one which won the ILS VRC challenge that we have seen earlier. And this also contains several convolution layers. There's a convolution layer here, then another one here, and here, and here. So there's so many convolution layers, and then some other type of layer. So the one which the network which won the ILS VRC challenge in 2012 is this one with the convolution network. So it's quite popular. So these are a more recent one. So you can go deeper, more hidden layers like this blue boxes here. So you can increase the convolution and you get a network. Or you can have several convolutions in parallel like this, and you can design your own filter size according to your task, and then you can connect them in different ways. So it's up to the problem at hand and the computation resources or other parameters decide how you want the design of your network to be. So this is a popular one. That's why it's just shown as an example. And this one is a popular one used in the biomedical community, where this is more for a segmentation task, you have to differentiate between different parts of the image. And this one is in the classification examples like this, you give an image and you get a single value at the end. This is for the segmentation network, you give an image, it will pass through these different hidden layers, and then at the end, and you get a segmentation of the result, and you can do a lot of things with that. This one is quite popular in the biomedical community. And recurrent neural network, that's another type of network. In the recurrent neural network, there are they form directed cycles with nodes. So in the traditional one, we have they form a directed cycle, so they form loops, and it sort of create an internal memory. And this is mostly used to process speech and text and video and so on. And a popular type of is called LSTM. This is a commonly used nowadays. Another type of neural network is called autoencoders. These are give an input, and you reduce the dimension of that feature, and until you reach a small encoded data here, and then you try to recreate the input from this code value. So they are they are a type of unsupervised feature learning method, and they are used in dimensional reduction, and you can stack multiple of them, and then you can create a deep neural network. This is not very much used in its original sense nowadays, but it is combined with other LSTMs or convolutional neural networks, and it's applied in new scenarios. Now we could go to the different components. So what are the different components of deep learning or deep neural network? So it contains linear algebra, then optimization, calculus, information theory, then parallel programming. So we'll go in detail all of this. In linear algebra deals with the matrix operation, like we have seen earlier, tensor operations, and we have like efficient routines like BLAS. We can apply for linear algebra operations. And then when it comes to optimization, we have this loss function. We have the loss functions are, we will explain that later. And we have the optimization space. Optimization space means how we the space where we optimize our parameters. So and how smooth the space is, it depends on the how effective our optimization is also, and things like that. These are like a heavily researched over several years, so we have quite a lot of tools to deal with these problems. We have to find the parameters, so like the most suitable optimized parameter. They could be like a millions of parameters like that, and we use stochastic gradient descent or its variants nowadays. Or we can also go for hyperparameter tuning. So these are like not the parameters of the network, but those extra parameters that we have, like we'll see later. And there are some problems of overfitting local minima or saddle points are like they are minima in one direction and maxima in another direction. So they are called saddle points. So there are tools to solve these type of problems. And also there is something called a regularization. So where we want to make our network not to overfit into the data. So that's we have some techniques. Then calculus. So in the calculus, we apply the chain rule of differentiation, which is an important part in this training of neural network. And we have matrix calculus. That means we have a huge matrix of derivatives. So we apply them in this backpropagation, that from the base of the backpropagation algorithm. And information theory, we have this loss function, different loss functions we have, and we try to reduce the KL divergence, where we try to find the similarity between two different distributions. So we try to model our network such that it can simulate the real data. So and we try to reduce the KL divergence so that we can get a better performance. And parallel programming we use, like we use GPUs, CUDA, OpenCL, and we have so many like hardware companies which supply tools and software for that. And even today's we have tensor processing units for even faster operations. Now we'll see how we can train a neural network. So how does the neural network learn actually? So neural networks are like a function approximator. So they transform input to output. So they are like they map. We give an input and we get an output. So it's like in between the input and output there is a neural network. So that will map the input to the output, and that's something called a forward pass in the neural network sense. So giving an input to the network is called a forward pass, and getting the output, that process is called a forward pass. The neural network learns from its mistakes. So we have to quantify the mistakes made by a neural network so that next time it will make less mistakes. So we use a loss function for that, and for quantification of the mistakes. And we find the effect of each and every parameter in making those mistakes. So that's what is coming in the backward pass. So we want to find the effect of each and every parameter so that less mistakes. So we have several parameters. What we can do with these parameters, like we can increase or decrease the value of each parameter so that it makes less mistakes. And that's what is done in a stochastic gradient descent. So in the optimization part. And we had to do this several times. And that's called the iteration. So we repeat this process: forward pass, loss calculation, then backward pass, and gradient descent, stochastic gradient descent. So repeat this process. So we have that's how we train a neural. The forward pass. So this is the schematic of what I have said. We have an input, we pass the input to the network, and it goes on like this. And at the end, there is a loss function. We have a label data. So label is actually ground truth, and that's what decide how the output of the network should be. And this loss function compare this label and output from this network and provide a loss, which is usually a single value. And this all come in the forward pass. Once we have done that, we calculate the gradient of this loss function, and then we go in this backward direction. We calculate the gradient of the next layer, and the next layer till we reach the first layer. And once we have the derivative of all these values, we update the parameter. So we have the parameter of the network, and then we make an update. So we change the values of the parameter once we have the derivative. So that comes in this optimization part. So we have seen like this is how the training of a neural network happen. So there are some real world things that we have to take care of. So in the different parts of training, the actual training, there's an actual training involved in the network. Then there is a loss function that we have to decide. Then we have to forward pass. Then we have the backward pass, and then gradient descent optimization. It would be the stochastic gradient descent that we have seen. We'll see in detail. So training. So for training, we need to have data. So usually neural network required quite a lot of data. So we have to partition the data into training, validation, and testing. It is important to divide your data into training into these different partitions. Otherwise, what happens is like if you train and test on the same data, you can get a real good performance because your network already know about your data, and then you test on the same data, it will give a good result. But when you have a new set of input, it will give a very bad result. So it's important to have your training data set as training set, validation set, and test set. So training set is the one which we actually train the data, and the validation set is used to get the performance of your trained model. So you train on this and you validate on your validation set and see if it's good or bad, and you make some changes in this training and then again repeat the validation process. And once you have satisfied with your validation result, then you test your network on a testing set. And this testing should be done only once. If you test more than once, then it will become a validation set. So it's something that we have to take care of while we train our neural network. And we have to do some pre-processing, which is usually like make the data 0 mean unit standard deviation, or change the image size so that it will fit in the GPU memory and things like that. And the important part is you have to design the neural network architecture. So what type of, how these convolutions or other layers are connected and things like that. And you need to have a hardware, like mostly it's a GPU you need to have to train the neural network. And you have to initialize the weights in the neural network. So we cannot start from like a 0 or symmetric values. If it's 0, then it will not learn anything. If it's symmetric, then different parts of the neural network learn the same values, and it's a little bit like redundant. So we need to avoid the redundancy. So we need to have like a non-symmetrical values. And there are several distributions we can take the initial values from, like Savior, MSRA, etc. And coming to loss functions, we have we had to decide the loss function that we have to use. We have like SVM loss, there's a hinge loss or softmax cross entropy loss or discriminator loss. That's a type of, that's another neural network actually. Any decision to make which one to choose is based on the problem at hand. So for most of the classification and segmentation tasks, we use softmax cross entropy loss because it's easy to optimize and it has got some nice properties. Or you can have like another neural network as a loss, which is called a discriminator loss. Or you can have other loss functions at your choice. So then it's the process called backward pass. So we know that we have to follow the chain rule. So traditionally what we have done is we find the analytical gradient of every component, like whether it's a multiplication or addition or an activation function, we have to find the derivative of each part, and then we need to find the gradient at a point, which is the product of the gradient at that node multiplied with the gradient coming to that. That's the chain rule. Basically, we'll see that in an example later. If we are connecting them to multiple nodes, we should add the gradient. So that it depends on how we connect the different nodes in the network. So if you use a ReLU activation function, that means a rectified linear unit. So we have seen it earlier. So this is an activation where it only passes the output to the positive output or 0. So we can cut out all these negative values. So the gradients also will pass only to the positive output where the input came from. So this is an example of this backward pass. This is a quite a simple function which involves some one addition and a multiplication. Assume this is our network. We have some input, we have operation in between, and then we get the output. So we have the input are x, y, and z. X is -2, y is 5, and z 4. We add these values, and you get a 3 here, and 3 is multiplied with the -4 to get a -2 here. So that's the forward pass. The green values are the forward pass. So now we had to find the backward pass or the gradient. So we can see this equation. So we can see here like f equals q multiplied with the z. So dou f by dou q is z. So derivative f with respect to q is this value here. And similarly, derivative of f with respect to z is q, the value here. And also we know that this equation is like a q equals x plus y here. And derivative of q with respect to x is 1 because it's a single value. And derivative of q with respect to y is also 1. And we have to find this value as well. So the derivative f with respect to x is f with respect to x. We have to find the derivative f with respect to q here, and derivative of q with respect to x here. So we combine these, multiply these two values. So we can apply these values in this equation and find the derivative. So we fix the last value as 1 because it is the derivative of f with respect to f itself. So that's 1, and then derivative of f with respect to q. So we know that value f with respect to q is z, which is here. So we already know that the input is -4. That becomes the derivative here. And derivative of q with respect to x is 1. So we get this value here, and similarly it's here. So similarly this value also we can get from this here. So that's how we find the backward pass. So you start from here and calculate the gradient at each intermediate levels and multiply with the gradient at that point, and you get the gradient at this point. So this is a simple example of backward pass. And once we have the gradients, or we compute all the gradients, we have to go for something called gradient descent, which is the optimization. So gradient descent is one way to optimize the objective function that we have, j theta. Theta is the parameter that we have. So it's the weight of the neural network. We have like several millions of this weight values. And we have to find the gradient of the objective function. That is the backward pass. We have to find the gradient, and then we have to update the parameter in the opposite direction of the gradient. So if we make in the same direction as the gradient, then we will get a gradient, higher gradient next time. So that's not what we want. We want to minimize the gradient next time. And we have something called a learning rate. So that decide how much change we should make on the parameter. So this is the initial parameter. You multiply the learning rate and you to the gradient, and you update the weights, and you get the new value. So this is the gradient descent. And there are different types of gradient descent. One is called a batch gradient descent. Another one is called a stochastic gradient descent. Then there's a mini batch gradient descent. So batch gradient descent means the full data set is is given in per update. So to make one change to the parameter, we pass through the whole data. So if we have like 1,000 images, then we have to give input to we have to pass all these 1,000 images to the network, and then update the parameter just once. That's like called a batch gradient descent. And in the stochastic gradient descent, we pass one image and then we compute the backward pass and then update the parameter. That's the stochastic gradient descent. So these are two extreme. One is like we give the full data set. The second one is like we give one image. And in between that is a mini batch. So in this case, we give a subset of data from like say 1,000. In the 1,000 set of images, we give like say 10 images. But we pass 10 images, calculate the gradient, and update. So we only pass the subset of the images. That's the mini batch gradient descent. So this is the most popular one used nowadays. So this is a schematic of how the stochastic gradient descent actually happens. So we start somewhere here of high gradient, and then during different steps, we pass through these different positions and then finally reach the minima somewhere here. So this is an illustration of stochastic gradient descent or the gradient. So we have seen that we have this learning rate. So it's an important hyperparameter that we have seen. So what happens is if we have very high learning rate, is like it decreases, the loss decreases quickly, and then after some time it will increase. So if we have a low learning rate, this loss decreases quite slowly over epoch. And if you have a high learning rate, it will decrease quite steeply, and then it almost stays there. And if you have a good learning rate, it is like it quite smoothly decreases over epoch. So epoch means the number of times we pass through the whole data set. So there's a difference between epoch and iteration. Iteration is the number of times we make update to the parameter. And epoch is the number of times we pass through the whole data. And we have other variants of gradient descent, like momentum. So we can add a momentum parameter so that if we have a momentum, then we move in the same direction of the gradient a little bit more before coming to a stop. Or we can go for an Estero accelerated gradient. It's also similar to this momentum. It will go a little bit further, and then if it's wrong, then it will make a change in the modification in the next iteration. So these are, and the ADA-grad, ADA-delta, ADA-musprop, ADAM, these are all different adaptive methods. So these are like the values, each and every values of the parameter changes independently of the other. So it's these are adaptive methods. If it's the gradient is higher, then it update more. If it's less, it's update less. So it's more adaptive. And these are all done to get a faster convergence, so that we get a loss function, loss value very fast. And regularization. So regularization is a way of reducing the overfitting to the training data. So what is overfitting means? If we train on the data and if it's overfitted, then when we test with our testing set, we get a very poor performance. So we have to reduce that, and so for that we use regularization. Data augmentation is a regularization technique. That means, say we have 1,000 image and we make some modification to the image, such as like a rotation or flipping and some spatial transformation, and you get more images. So that's an example of data augmentation. Then there's something called a dropout. Dropout means we have seen like several layers are connected. So in dropout, we randomly drop some connections so that not all neurons are connected to every other neuron. And this is like a random, and it changes every time we make a forward pass. Or we can go for batch normalization, which is more like a zero mean unit standard deviation type of normalization. Or we can go for batch-wise learning, that's a mini batch that we have seen earlier. So we can change this batch size to get a optimal performance. Or you can have like other type of normalization, like a local response normalization or L1, L2 regularization of weights. So L1 means we give more importance to some parameters and less importance to some other parameters. Or you can have like a L2 regularization where you give equal importance to every parameter in the network. And then there is a hyperparameter learning. So the learning rate that we have seen is a hyperparameter or learning rate decay. That means you can change the learning rate over epoch. Then there is a momentum term. If you want, you can have momentum or not. Then network depth. Usually network depth means the number of hidden layers we have. And network width is a number of filters per layer that we have. So we can change these values and see which one is giving better. We can vary the mini batch size also. So these are some of these hyperparameters that we have to take care of. Okay, we have seen how the neural network works and how we can do the training process and everything. Now we'll see an implementation of how we can do that. So all the implementation aspects. So how we can implement this neural network. There are so many tools available. One is called a PyTorch from Facebook. Then there is a TensorFlow, MXNet, ML.NET, DL4J. These are different tools available nowadays. And these top two are based on Python. So all of them are open source. So you can use any of these tools available. And we even have some hardware accelerators nowadays from different companies like NVIDIA, Intel, Google, HTTP, or you can even program your own FPGA for your own task. You can have a hardware implementation of your neural network also. So this is an example code. So if you examine this code, look carefully. So this is an enumerator which we load the data set. And here we get the actual data. So in the data, you have the input, you feed to the network, and you have the label or the ground truth that you give to the loss function you have. And then you make some zero gradient to the optimizer so that you can start. And then here is the actual process. So net is the network that you have designed, and then you pass input to the network and you get the output. And once you have the output, you pass the output to the criterion is the loss function. So they call it criterion. You can design which criterion or loss function you want. So in the loss function, you give your output from the network and the label that you already got from your data, and you get a loss value. So this is the loss that you get, and this is a single value. And then with this single line, like a loss dot backward, you perform the backward back propagation or backward pass. And then once you have done that, then you change the update the parameters, the stochastic gradient descent that we have seen. So it is called by optimizer.step, which is so you can see like just in 4 lines of code you can train a neural network, and you repeat this process several times using this for loop. So it's any of this modern deep neural network tool is something similar to this one, and it's very easy. So you don't have to calculate anything, any of this gradient or anything by hand to train your network. So it's very easy to do things nowadays. Okay, we have seen how we can train a network, and so a word of caution, I should say. So something called a bias. This is an example that we did some years ago, and the problem to solve was like a classification problem. It seems quite simple. So what we had to do is we have to, in this image, we had to classify this bent tail. This one is having a bent tail, and this one is having a straight tail. So you just have to identify if the fish is having a bent tail or a straight tail to make the classification. So we trained a neural network, and we got a very good accuracy and everything. And we thought like, okay, network is able to detect this bendness in the tail. So then we did some further examination of what actually is the network learning, and then it was a little bit of surprise to us. So here we can see the probabilities of different input. So this we call as deformation probability. So we give an image like here. The row is like the light green, and the probability is here. So these are like this part is the treated image, and these are the untreated image. So treated image are like they give a bent tail. And we can see that when we give the raw image, we get a high probability here. This bar is quite high in this case. These are different images. So this one image, this second image, third image, and so on. And when we give an image with the tail alone, like we covered or erased the head part of the fish and give the tail only. So here for the same image. And to the surprise, we see that the deformation probability is quite low. So we initially thought like the neural network is detecting the bendness of the tail, but it is not able to detect the bendness of the tail if we give the tail alone. So that was a bit surprise. Then we erase the tail part and give the head part of the fish alone. So this part. So erase the tail and give the head alone. And that's this one, and that's the head only. So again, when we saw that when we give the head only image, the probability again increases. So that means the neural network is not looking at the tail of this fish, but at the head of the fish. So that was a little bit of a surprise. So then we further examined this the literature and found that when we treat the fish with this particular drug, its head also changes a little bit, but it's a little bit difficult for a layman to see that small change. So the neural network was able to detect something that that we were not expecting. So this is something we always should remember especially when we try with the medical images. So we always test our network thoroughly before going for some sort of implementation, because it might be finding something else than we actually want them to detect. So this is a little bit of a word of caution, I have to say, since we are talking about AI in healthcare domain. So yeah, I think that's my last slide. Thank you so much for your attention. I think we can go for some question now.
Thank you, sir. Thank you for the informative session, sir. We are having some questions, sir. Shall I ask you now, or else you can see in the forum right now? Are you able to view the questions, sir? If you are not able to view,
yeah, you can ask the questions, or should I go for this QA?
How are the weights assigned, sir? Whether there is any process for assigning the weights? It's a first question.
Yes, we can assign weight. We can assign weights using different distributions. Like there are popularly available. It's more like a Gaussian distribution with some variation. So there are something called a Savior or MSRA, or there are a few others. So it's I can't remember the exact name, but there are, if you search for like a neural network weight initialization, you get a lot of different distribution you can use, and then you can initialize the weights from those distribution. I hope that answered that question.
Sir,
And the second question is how to choose a specific activation function for an application. So this choosing an activation function is, it depends on the problem at hand. So most of the cases, like when we apply classification or segmentation, we can blindly choose rectified linear unit ReLU activation function. But if we go for the problems like image generation using generative adversarial network and things like that, so more advanced ones, then we have to carefully choose the activation function. So most of the time, sigmoidal activation functions are chosen. So it depends on the problem at hand. We decide the activation function.
one more question, sir.
Yes, sure.
Sir, please provide the benchmark breast cancer image dataset links for classification in benign and malignant tumors, sir.
If you can type the question, then it will be easy.
They asked it in the chat box. That's a reason. Okay, you please answer the questions in the QA, sir. Yes,
so
some more questions are there.
I can type the answer maybe. So another question, or did you ask about the benchmark dataset? I think most of the datasets are available open source in nowadays. I forgot exactly how to search for the dataset. I think there is a tool from Google itself. There is like a dataset searching tool. So you can use that Google dataset searching tool to get many of this dataset available. How to classify epilepsy using EEG signal. So I'm not able to type on that one, but I haven't worked with the EEG signals, but I'm sure that you can apply some of this LSTM type of neural network. So where we use a sequence of data to classify this EEG signal. I think that's where you start with. How to separate training test data from the data set. So what we usually do is like we go for 5-fold cross-validation. So the easiest way is when you have say 1,000 images, first thing that you make a random selection and choose say 750 from the image as the training and 250 as the test. So don't touch the test set and take the training set and then you go for a cross validation, like say 5-fold cross validation. That means you divide this 750 subset of images into 5 smaller subsets, and you have five sets, and you take out one of the subset and combine the rest of the 4, and take the 4 of this subset and use that as a training set, and this one as your test set. Not test set, as the validation set, sorry. And then you take out the second one and combine the rest of the 4 and use this as the validation set and the rest as a training set. And you repeat the process for each and every subset of this 750. And then you train your, you have 5 different subset of your training and validation set. You train your design neural network 5 times and see the one which is having the best performance out of this 5. And that will be the best model that you have. And then you apply this best model on your test set that you have already separated from the 1,000, like the 250, say, for example. And then check the performance on that. That's how you separate your training data set. Age, gender detection data set. So these are like those age and gender that slides I have shown is, I have provided the reference at the bottom, so you can check those paper to get further information. So all of these examples I have a reference at the bottom or at the end of the slide. What will be the value of fan in or for a large number of input? It's difficult to say the number of input that you have. It depends on the number of input is more like the size of the size of the image that you feed. So usually we give any image of size, say 256 by 256 or 224 by 224 or something like that. So it's not a very large image, it's a very small image if it's image analysis task. And it also depends on the GPU that you have. If you have a very large GPU with a lot of memory, then you can give a large image, and otherwise you have to give a small image. What could be the reason for negative pixel value when recovering pixel array from DICOM image? I think it's probably some float value that you have in the DICOM image. I'm not exactly sure, but if you have a negative value, then it would be a float value, and you carefully choose the conversion from float to integer or other other values. So I think that's the reason mostly. Exactly in which situation biasing is done. It's the bias is done because it depends on the data that we have. Also the network mostly depends on the data. So assume that we have a distribution of your some sort of a Gaussian distribution, and you have a large Gaussian distribution and a small Gaussian distribution, and you sample your data. And if your data samples are from the smaller Gaussian distribution, then your data will be like, or your training model will be biased towards that small one rather than the large one, huge Gaussian. So what you want to do is like don't want to have don't want your data to drag towards that one. So that's roughly how biasing happens. It's difficult to see if it's biased or not. The only way we have is like we go for some ablation studies or go for the cross validation that I have mentioned. So you see if it's any biasing is there. Is there anything like fan out for input and output for a neural network? I don't exactly know about the exact the fan in fan out values. I think there is some sort of a calculation some time ago. I don't exactly remember, but probably one can Google for that one. That's specific. Yeah. So I think we have 2 more minutes. I guess if you have any questions, or you can. I have shared the slides with the organizers. So if you have any questions later, you can mail me also.
Thank you, sir. Thank you for sharing your knowledge, which is from the basic to the very advanced level. I think it will be very useful for the people who are going to do the research in this area. Thank you, sir. Thank you for your address as well as this mind-provoking section. Thank you so much, sir. Thank you for your valuable time, sir. Dear participants, tomorrow we will share a different Zoom link as well as YouTube link for the tomorrow session. Tomorrow's session will be handled by Dr. P. Vijayalakshmi, Professor, Department of Electronics and Communication Engineering, SSN College of Engineering, Chennai, Tamil Nadu. We shall meet you tomorrow at the same time. Thank you all.